Welcome to a video on solving trigonometric equations. In this lesson, we'll look at just solving basic equations using just kind of some simple algebraic techniques. And then we'll come back in another video in a few weeks and look at how we can incorporate all those identities that we just learned about. How do we use them to also solve equations? But for now, we just want to kind of look at what does it mean to solve an equation, and again, just some of the basic ideas. When we solve an equation, there are two ways that we can express the solution. One is we can express just all the answers, and there could be more than one, there generally will be more than one, but all the answers between 0 and 2 pi. And so if you remember, 0 to 2 pi is going to represent one complete loop, one complete cycle around the unit circle. And then we also have a technique that we use to express the fact that there are actually infinitely many solutions, because you could keep going around the unit circle forever in both the positive or the negative direction. So let's look at the overall process that we can follow to solve trig equations. And again, we won't look necessarily at all these points, but we'll look kind of at most of them in this video. So the first step that you would want to do is to simplify your equation. Okay. Now, again, right now, that's primarily just going to be an algebraic process. We're going to look at specifically, just some simple arithmetic, adding and subtracting numbers back and forth, dividing numbers, or factoring, maybe some square roots, stuff like that. And then in a few weeks, we'll come back and we'll look at how do we take the identities that we just learned and combine that into this process. But for now, it's just going to be kind of basic algebraic stuff. And we're just going to simplify it. When you have the identities, you want to make sure you have the equations all written in terms of sine, cosine, and tangent. So like you have those reciprocal identities that would let you convert, cosecant to sine. So once we have our simplified equations, and we have them all in terms of sines, cosines, or tangents, we want to determine the solution for the sine, cosine, and tangent equations in one period. Okay. Now, when we think about the period length for sine and cosine, remember that's a period length of 2 pi. If you remember back to our graphs, and again, that represents a full loop around the unit circle. Tangent's a little different. Tangent has a period length of only pi. And so when we talk about the answers in one period, we really only have to find the answers. Depending on the textbook you read, it may say finding the answers from negative pi over 2 to positive pi over 2, because that's usually kind of the standard period. Or you could talk, and that's the way we'll do it, is we're going to talk about how do you find the answers just between 0 and pi. That way we keep our values all positive. So usually for sine and cosine, we're looking between 0 and 2 pi. For tangent, in the larger scope, you only need to look at answers between 0 and 1 pi. But ultimately, we're going to want answers everywhere. So once we can kind of find those answers, we want to look at how we can express all the solutions. Okay. And so we do that by adding this we call it an arbitrary constant. In this case, we use the letter K. Some texts may use the letter N or a different letter. But K just represents an integer. So if you remember, integers are all the positive and negative whole numbers. So 1, 2, 3, 4, 5, 0, and negative 1, negative 2, negative 3, and so forth. So what we do is, again, remember that sine and cosine have a period of 2 pi. So that means going once around the circle, if you keep going another time around the circle and another time around the circle, you'll keep ending up at the same spot on the circle. Right? We have those coterminal angles. And so for sine and cosine, we're going to, to our answer, we're going to add a little expression. We're going to do plus 2 pi k. Okay? So that plus 2 pi k just shows us that there are, in addition to the one specific answer we list, there are infinitely many coterminal answers to that. Again, it's just going one more time or 2 more times or 3 more times around the circle in either the positive or negative direction. Again, that's because of k is an integer. And then for tangent, again, tangent has a period of just 1 pi. So instead of adding 2 pi to the answer, we'll add just a pi k. All right, and so we'll see what that looks like in practice here in a few examples. And in addition to listing all solutions, we want to be able to list any specific solutions that are on the interval from 0 to 2 pi. So within one cycle of the unit circle, what are all the answers? And sometimes we may kind of, steps 3 and 4, we may flip around a little bit and kind of merge them with step 2 a little bit. So it's not necessarily like real extinct steps here that we're kind of doing each one separate from the other. It's just you can kind of interplay some of these steps with each other a little bit. So let's just work through a bunch of examples here. We'll start out again fairly easy, just doing some basic algebra, and then we'll look at some examples that involve maybe square root and then some factoring. Okay, so for this first example, we want to determine any solutions on the interval from 0 to 2 pi. So remember that was the last step in that process, but we can again change that order around a little bit. But we want to find any solutions on the interval from 0 to 2 pi, and we want to state the expression that represents all answers, the infinitely many solutions. Okay. For this first example, we have 3 plus cosine of theta is equal to 2. So in order to solve the equation, again, remember our first step was to simplify the equation. And so when we want to simplify it, if you just think about solving a normal equation, so say just go back to like an algebra class. If you had 3 plus x was equal to 2, in order to solve it, you would isolate your x, right? So you'd subtract 3 from both sides, which the 3's on the left side cancel out, and you're left with x is equal to a -1. So we're in essence doing the same thing. We're going to solve it in terms of cosine of theta first. So we have 3 plus cosine of theta is equal to 2. We're still just like we would in algebra. We're going to subtract 3 from both sides, which that leaves us with the cosine of theta is equal to a -1, just like it did before in algebra. So this is where the trig comes into play. We want to find any values for theta that makes cosine of theta equal to a -1. And to do that, again, we want to think about our unit circle. So let's go ahead and just draw out, make a rough sketch of our unit circle. Okay, so we want to know when cosine is a -1. So remember, cosine is the x-coordinate. So we want to know which points on the unit circle have an x-coordinate of -1. It turns out that that is one of the quadrantal angles. It's on the negative x-axis, and that is an angle of 180 degrees. Well, we don't want to deal with degrees since we want to look for the answer between 0 and 2 pi. We want to think of this in terms of radians. So pretty much all of our work in here is going to be in radians. So the angle to the negative x-axis is going to be pi radians. So we know that theta has to equal pi. Okay, so that's the only angle between 0 and 2 pi, the only number between 0 and 2 pi that will make cosine equal to 1. So theta is equal to pi. This is the answer that we have on the interval from 0 to 2 pi. Okay, so that's the first part of our problems. We want to figure out that solution. The second part is we want to state the expression that represents all solutions. So if you remember on the previous slide there, we talked about how we could add an additional expression, and for sine and cosine we're going to do plus 2 pi k. So what our answer would look like, again, it's really easy. We're just going to put that 2 pi k on the end. So we're going to have the original pi plus a 2 pi k. Okay, and this is the answer for all solutions. So what exactly does that mean? Well, let's go back to our unit circle here. So according to our first answer, we know that if we were to rotate along the unit circle for pi radians, we would end up with a point on the unit circle. And that point on the unit circle has a coordinate of -1, 0, and cosine of pi then has to be a -1. So that satisfies the original equation that we had. But what happens if we continue to rotate? How far do we have to rotate to end up at the same place? So if we start that rotation of pi, and then say we rotate another distance of 2 pi, well, it turns out that I end up at the same point. And what if I were rotating again another distance of 2 pi? Well, I'd end up at the same point. And if I rotated again a distance of 2 pi, I'd end up in the same point. What if I rotated in the other direction a distance of 2 pi? Well, I'd end up with the same point, but now it's a -2 pi. And so anytime I rotate an additional 2 pi, whether in the clockwise or counterclockwise direction, I will still end up at the same point. And so that means any point that has pi plus a multiple of 2 pi, I will always end up here on the negative x-axis at -1, 0, and those are all points that make cosine equal to a -1, which makes 3 plus cosine equal to a 2. So, and there's infinitely many times that I can rotate around this, and so that's why we can't obviously express an infinite number of answers by listing them out. So we need an expression that summarizes that, and that's what this plus 2 pi k is. Okay, it gives us a summary of all of those infinitely many answers. All right, let's look at another example. So we have 2 times the sine of beta is equal to the square root of 2. And again, we want to find all the solutions between 0 and 2 pi, and then we want to state all solutions for the infinitely many rotations around the circle. So again, our first step is to simplify. And again, we're just doing basic algebra here. So we could go ahead and divide both sides by 2. And so that's going to give us the sine of beta is equal to a square root of 2 over 2. So once we've simplified it, we pretty much have to go back to our unit circle every time. That's the whole point of this, is to simplify it down to a nice, simple expression involving sines, cosines, and tangents. Hopefully it's a number on the unit circle, which we can find the exact solution. If not, we may have to use our calculator. So let's think about where sine is equal to a root 2 over 2. So we know sine is positive in the first and the second quadrant, and this is a positive root 2 over 2, not a negative root 2 over 2. And so we know that sine is a positive root 2 over 2 at 2 locations. It will be a root 2 over 2 when beta is a pi over 4 radians, or when it is 3 pi over 4 radians. And so those are the two answers that we are going to get. So we get beta is equal to pi over 4, comma 3 pi over 4. And again, those are the answers. Those are the only answers between 0 and 2 pi. Okay, so those are the answers on the interval from 0 to 2 pi. So how do we express the fact that there are infinitely many answers? So again, we're going to take each of these and we're going to add in that little extra expression. So we have beta is equal to pi over 4 plus 2 pi k. And we're going to have a second expression. We're going to have beta is equal to 3 pi over 4 plus 2 pi k. And in order to express all of the solutions, we have to have both of these expressions. Okay? If you didn't write the second one, if you only wrote the pi over 4 plus 2 pi k, you would only get the angles that are coterminal in the first quadrant. And if you didn't do the pi over 4, but instead wrote 3 pi over 4 plus 2 pi k, you would get the infinitely many answers that are coterminal in the second quadrant. but we have both of these that we have to include. So make sure that we have both of these as your answer. Now we may eventually see some problems where it is possible to combine these, sort of merge them into just a single expression, but neither of these examples we've looked at so far would allow us to do that. All right, let's look at a third example, this time involving tangent. So we have 3 plus 5 times the tangent of x is equal to 8. So again, our first step is just basic, simple algebra right now. We'll get into more complicated stuff later. But again, just treat this like a normal algebraic expression. If we're trying to solve for x, we need to isolate it, which means we need to move stuff around back and forth. So the first step we're going to do is subtract 3 from both sides of the equation, and that leaves us with 5 times the tangent of x is equal to 5, and then we're going to divide 5 into both sides of the equation, and that's going to give us the tangent of x is equal to 1. So we just 2 steps of algebra, and we got it simplified down to a nice and easy trig expression involving tangent. And so now we want to think in terms of the unit circle. So we want to know, when is tangent equal to 1? Well, we know tangent's positive in the first and the third quadrants. Since we have a positive 1, we want it to be positive. And remember, tangent is y over x, and so we want the points where the y and the x coordinates are the same. So in the first quadrant, again, just using our unit circle, that's at pi over 4 in the first quadrant, and then in the third quadrant, that would be 5 pi over 4. So there's 2 answers between 0 and 2 pi. So we would have x is equal to pi over 4, comma 5 pi over 4. And you could write those separately, x equals pi over 4, and then x equals 5 pi over 4, but you can kind of merge them together. Again, this is the solution. Those are all the answers on the interval from 0 to 2 pi. So how do we express the infinitely many solutions? Well, with tangent, we can kind of do this in 2 ways. One, we could take each of those solutions and add a 2 pi. So x equals pi over 4 plus 2 pi k. And then we could also say x is equal to 5 pi over 4 plus 2 pi k. But we have, particularly with tangent, and particularly in this case, we have a better way of doing that. Okay, and if you remember, with tangent, instead of adding a 2 pi k, there are actually 2 things that I mentioned in that list of the process that we can follow. There's 2 things I mentioned that we haven't kind of talked about here. One is, when we talk about tangent, we only need to look at answers between 0 and pi. And then the second part is that we're only going to add a pi k. Okay? So for the 2 answers that we had, pi over 4 and 5 pi over 4, we only need to keep pi over 4. We only need to keep the first one because that's the only one of the 2 that's between 0 and pi. 5 pi over 4 is bigger than pi. So we could express so far this as x is equal to just pi over 4. And then the second part is, instead of doing plus 2 pi k, we're just going to add in a plus pi k. Okay, so why can we express our answer this way? So why can we just express our infinitely many solutions using the 1 expression for tangent and then the plus pi k? Well, to understand that, let's go back to the graph, to our unit circle. We know one is at pi over 4 and the other is at 5 pi over 4. Well, how far is it from, if we follow the unit circle, from pi over 4 to 5 pi over 4? Okay, so from a 1 pi over 4 to a 5 pi over 4 is a distance of 4 pi over 4, which turns out to be pi. And so how far is it from 5 pi over 4 back to where the point at pi over 4 would be if we kept going counterclockwise? This would actually be 9 pi over 4 if we kept going around, if we kept counting, so we'd have 9 pi over 4, but it's still a distance of pi. And every time, so I mean, if you look at these 2 points are exact opposites across the origin from each other. They form a 180-degree angle, so they're a straight line. So that means it's always a distance of pi from the first point to the second, from the second to the third, or coterminal back to the first, from the first to the second, from the second to the first, from the first. And so we can just keep going around and around and around by starting at the first point and then adding a distance of pi, you get to the second. And once you add another pi, you get back to the first point, or coterminal to the first point. So that pi, because tangent only has a period of pi, we don't need to include all the answers. If we did, we'd actually have we would be repeating answers. So we only need to list any answers between 0 and pi, and then do a plus pi k for each of those. All right, let's look at another example. So we have 3 times the sine of theta is equal to 1. So let's just do algebra again here. To get sine by itself, we're going to divide both sides by 3. So we get the sine of theta is equal to 1/3. And so at this point, we need to stop and think. So we have it simplified as far as we can go. But 1/3 is not one of our unit circle angles. So how do we go about finding when sine is equal to 1/3? Well, let's pause on that for a moment and let's think about roughly where it will equal 1/3. So let's talk about the unit circle here. Where is sine positive? Well, it's positive in the first and it's positive in the second. And remember, sine represents the y-coordinate. So somewhere on our unit circle, in the top half of the unit circle, we have 2 points, one in the first quadrant and one in the second quadrant, where the y-coordinate is equal to 1/3. Okay, so how do we find that angle? Well, we've looked at a method to do this a couple weeks ago. If we're trying to find the angle and it's not a unit circle value, we can use inverse sine. So we could solve for theta by computing the inverse sine of 1/3. Okay, so again, inverse sine, it represents the angle whose sine is equal to 1/3, which is what we're trying to compute to begin with. Now, since 1/3 is not a unit circle angle, we're going to have to do this using our calculator. So if we type in the inverse sine of 1/3, and we compute that, let's make sure that we are in radian mode. We don't want to be in degree mode, we want to be in radians. The inverse sine of 1/3 is 0.3398. So we get theta is equal to 0.3398, and it's in radians, so I'm not going to put the degree symbol. Okay. Now here's the thing. How many solutions are there supposed to be? There's supposed to be 2, one in the first, one in the second quadrant. But when you do inverse sine, remember, inverse sine is only going to give you an answer in the first or the fourth. Remember, when we compute inverse sine, our angle is going to be between a positive pi over 2 and a negative pi over 2. So it's actually going to be in the first quadrant as a positive value, or it's going to be in the fourth quadrant as a negative value. So since this came out to be a positive 0.3398, I know that it's in the first quadrant. So how do we find the second angle? Well, let's think about what that 0.3398 represents. It is the angle from the x-axis to the point on our circle. So this angle here is at 0.3398. Okay. And if you remember the way we developed the whole unit circle, that is an acute angle. And so the second angle in the second quadrant, it has to have an acute reference angle that also extends down to the x-axis. And that angle there is also 0.3398. So how do we find the total angle? Well, the total angle would rotate from the x-axis to our actual point. Okay, and that's the angle we're trying to find. So theta. Theta is the rotation, we'll call it just theta again. Theta is the rotation from the x-axis to our second point. And we know from the second point to the x-axis is 0.3398. So that means if we did theta, our second angle, plus we'll say 0.3398, what is the total of that rotation? So if we rotated from the positive x-axis, we rotated a distance of theta to the second point, and then we rotated a 0.3398, where do we end up? We'd end up on the negative x-axis. So what rotation goes from the positive x-axis all the way around to the negative x-axis, which is half the circle? It's a distance of pi. So if we solve that for theta, we're going to get theta is equal to pi minus 0.3398. And we can compute that on our calculator. So if we compute pi minus 0.3398, we're going to get 2.8018, depending on how you round it. So that gives us our second answer. We know theta will have two answers, either 0.3398 or 2.8018. And again, those are the solutions only on the interval from 0 to 2 pi. Okay, so how do we find all the solutions? Well, we do it the same way we did before. We're going to have to write for each of the two answers, we're going to have to add a plus 2 pi k. So we're going to have theta is equal to 0.3398 plus 2 pi k. And we're also going to have theta is equal to 2.8018 plus 2 pi k. And together, these two statements represent the infinitely many solutions as we rotate around and around and around the unit circle. All right, let's look at another example, this time involving tangent again. So same process, we want to find all the solutions on 0 to 2 pi, and we want to state all the infinitely many solutions. So for this example, we have 7 minus the tangent of x is equal to 9. So to get tangent by itself, we're going to subtract a 7 from both sides. So we're going to be left with a negative tangent of x is equal to 2. And then we want to multiply both sides by -1 just to move that sign over. So we have tangent of x is equal to a -2. All right, so we've got it simplified. So we're ready to use the unit circle if we can. So how do we find when tangent of x is equal to a -2? Well, is that a value on the unit circle? And the answer for that is no. So this is not on the unit circle, at least not one of our exact values. So we're going to have to use, just like we did in the last example, we're going to have to do an inverse tangent. So x is going to equal the inverse tangent of a -2. So if we compute the inverse tangent of a -2, we're going to get x is equal to a 0.1071. And that's rounded to 4 decimals. Okay, so how many answers are there between 0 and 2 pi? Well, let's think about where tangent is positive and negative again. So do we want to know where tangent's positive or where tangent's negative? Well, based off of our simplified equation, we have tangent of x is equal to a -2. So we want to know where's tangent negative. Well, it's positive in the first and the third, which makes it negative in the second and the fourth. So this -1.1071 is an angle down here in the fourth quadrant, and since it's negative, it is rotating clockwise down into the fourth quadrant. Okay, now, and this -1.1071, it's not even itself on the interval from 0 to 2 pi. So that's not actually going to be one of my final answers. It's not within the interval that we want. So how do we find the answers that are? Well, and again, this is going to involve, the nice thing with tangent is we just need to go halfway around the circle. So if you're in the fourth quadrant, you can get into the second quadrant by adding pi, because it makes a 180-degree angle. So if we rotate a distance of pi from my given answer, I will end up in the second quadrant, and it will actually be positive now. And so how do we find the second answer that's between 0 and 2 pi? Well, again, the nice thing about tangent, take the answer we just got and add another pi to it, or add 2 pi to our original answer. Okay, so again, it's always just rotating around half the circle. So to find our first answer, let's take our the answer we got from our inverse tangent, a -1.1071, and let's add pi to that. And if we do that, we will get 2.0344, and again, that's rounded to 4 decimals. So this is the answer in the second quadrant. Well, how do we get the fourth quadrant? We're going to add another pi to that, and that's going to give us 5.1760, again rounded to 4 decimals. That's the answer in the fourth quadrant. Okay, so what are my solutions between 0 and 2 pi? So we know x would equal 2.0344, and we know it's also equal to 5.1760. So those are the two solutions that we get on the interval from 0 to 2 pi. So again, this was a little harder because the first answer we got, that -1.1071, was not even one of the two answers we wanted to keep. It was, we had to use it to get to the answers that we wanted, because again, this number, -1.10171, is less than 0. It's not between 0 and 2 pi. So we have all the solutions from 0 to 2 pi. How do we express the infinitely many solutions? Okay, well, first, again, remember that our two answers, the 2.0344 and the 5.1760, both of those are a distance of pi away from each other, the way that we have this rotation going around. And we could rotate in the other direction too, but we know they're a distance of pi. And we also know that when we show our infinitely many answers, we only need to do a plus pi k. We could list both of these out and do plus 2 pi k, but we want to have a nice clean answer. So we only need to keep that first one. So x is equal to 2.0344 plus pi k. And so that expresses all of our solutions. Again, we don't need to keep both if we do the plus pi k, because it's you're always adding a pi, just like we found the 2.0344 and the 5.176. We're just adding pi over and over and over again. So just using the one answer will then generate all the other answers that we need. All right, let's look at one more answer with just kind of the basic algebra, but this one's a little different. So we have cosine squared of theta is equal to 3/4. So it's a little different because we have a square in it. Now when you see the square, again, you might be tempted to use an identity, right? We have the Pythagorean identity. We have the reduction and identities, but we're not going to worry about identities right now. We're just going to do some algebra. So let's just think for a moment. If I had the equation x squared is equal to 3/4, how would you get x by itself? Well, you'd take the square root of both sides of your equation. And so we would get x, because the square root of x squared is just x, equals the square root of 3/4. Now, and one other thing to keep in mind, when you take the square root of both sides of an equation, you will get a plus or minus. And the square root of 3/4, you could simplify to plus or minus the square root of 3, then divided by 2, because the square root of 4 is the 2. So we get plus or minus root 3 over 2 as x. Okay, but again, in our problem, we're not trying to find x, we're trying to find theta. So we have the cosine squared of theta is equal to 3/4, but same idea. We're going to take the square root of both sides, and so that's going to leave us with the cosine of theta would be equal to plus or minus a square root of 3 over 2. So pause for a second. Is square root of 3 over 2 one of our unit circle values for cosine? Yes, it is. Okay, so we can come up with exact values. We don't need to use our calculator. And then we also need to think, where is it positive and where is it negative? Because when we have this plus or minus, we can actually break this apart. We have two equations technically. We have the cosine of theta is equal to a positive root 3 over 2. Or we also have the cosine of theta is equal to a negative root 3 over 2. Okay, so there's two different ways that this plus or minus converts us into two separate equations, and we need to come up with answers for both of those. So let's go over to our unit circle and our quadrants. Where is cosine positive? Again, cosine is positive in the first and the fourth, so it is negative in the second and in the third. And when is cosine root 3 over 2? It's a 30-degree angle, which is pi over 6. So we want the pi over 6 angles in the first and the fourth quadrant. So pi over 6 and then an 11 pi over 6, because that puts us another one down here in the fourth quadrant. So these are the positive two. We're also going to have one in the third or second and one in the third quadrant. So the pi over 6 angles over on the left side are going to be 5 pi over 6 and 7 pi over 6. So those are the four angles on the unit circle from 0 to 2 pi that produce either a cosine of either a positive root 3 over 2 or a negative root 3 over 2. So that means theta is going to equal all four of these. So we're going to have theta is equal to pi over 6, pi over 6, 7 pi over 6, and 11 pi over 6. So all four of these together represent the solutions on the interval from 0 to 2 pi. All right, so how do we then express the solutions for all solutions? So how do we express the fact that there's infinitely many? Well, it's cosine, and so for cosine, we're just going to take all four of these and put on a plus 2 pi k onto them. So we're going to have four of these statements. So we're going to have theta is equal to pi over 6 plus 2 pi k. We're going to have theta is equal to a 5 pi over 6 plus 2 pi k. We're going to have theta is equal to a 7 pi over 6 plus 2 pi k. And then we're also going to have theta is 11 pi over 6 plus 2 pi k. All right, and so all four of these, again, all four of these together represent all solutions. Now there is a little bit of simplifying that we can do here. Notice that pi over 6 and 7 pi over 6 are opposite angles. They are straight across from each other. So that means from pi over 6 to 7 pi over 6 is a distance of pi. Okay, so if I had pi over 6 and I added pi to it, I would get a 7 pi over 6. And if I took that 7 pi over 6 and I added a pi to it, I would get at 13 pi over 6, but that's the same thing as pi over 6. So these are both just kind of like tangent. These two, the pi over 6 and the 7 pi over 6, they are distances of pi away from each other. And in sort of a similar way, the 5 pi over 6 and the 11 pi over 6 are a distance of pi away from each other. Okay, so if you had 5 pi over 6 and you added pi, you'd get to the 11 pi over 6. And if you added 11 pi over 6 plus pi, you would get a 17 pi over 6, which is the same thing as 5 pi over 6. So what that means is we can take these four expressions that we had for infinitely many answers, and we can merge them into just two answers. So the first one would take the pi over 6 and the 7 pi over 6, and we could write that as theta is equal to pi over 6 plus pi k. And again, it's a pi because that's how far it is between these two answers. So that takes care of the pi over 6 and the 7 pi over 6. The other two, the 5 pi over 6 and the 11 pi over 6, those we could write based off of the 5. So we can have theta is equal to 5 pi over 6 plus, so how far is it from 5 pi over 6 to 7 or 11 pi over 6? It's a distance of pi. So again, we're going to have a plus pi k, and that takes care of the 5 and the 11. Because again, if you take a 5 pi over 6 and you add a pi, that will give you an 11 pi over 6. Same thing with pi over 6 plus a pi, that would give you the 7 pi over 6. So we could express, instead of using all four answers to express the infinitely many solutions, we could use just those two. Now, I don't care which way you do this, like in the lab manual and stuff like that. I think oftentimes in the lab manual it will show you the second version of those four answers as two. But there's not necessarily a correct way to do it or not. Using just the plus pi over k is usually probably the simplest answer. So if you're looking for the simplest answer, that's what it would be. All right, so let's look at a few examples involving factoring. And so we're just going to look at finding all the solutions to the equation. So this first equation, it's 2 cosine squared of x is equal to x. And I really like this example because it's going to illustrate a common mistake that too many people make. To see what I mean by this, let's look at this as just a simple algebraic equation. So let's get rid of the cosines. What if we just had 2x squared is equal to x? And again, sort of a common mistake people are going to make is when they see an x on both sides of the equation, they're going to divide both sides by x, which on the right side gives you a 1, and on the left side the x is reduced down a little bit, so you're just left with a 2x. And then solving for x gives x equals 1/2. Okay, so if you were to plug that half into the original equation, it would actually work. 2 times a half squared, which a half squared is a fourth, 2 times a fourth is a half, so it will actually work. But there's one more number that will also work in this equation. If I plug 0 in for x, I'll get 2 times 0, which is 0, is equal to 0. Okay? So we also need to have a second solution, and that's 0 equal to 0. So if x is equal to 0, we get a solution. So the point being here is that just because we have an x on both sides of the equation, we don't want to divide by x, okay? Because it could be possible that we're dividing by a 0, and if we do that, we're going to lose that 0. Okay, so if we divided by x, we would have lost x equals 0 as one of our solutions. So the better approach to solving this kind of equation is don't divide. So instead, we want to take 2x squared is equal to x, and we want to subtract the x to the other side. So that means we're going to have 2x squared minus x is equal to 0. And now, instead of dividing, I can factor, which is a sort of division, but we're not technically dividing it out. So if I pull out an x, I'm going to have x times the quantity 2x minus 1. And we know from algebra, if you multiply two expressions and you get 0, then we know one or both of those equations, one of those parts is equal to 0. So either x equals 0, or we have 2x minus 1 is equal to 0, which if we solve that for x, we will get the half. So by doing it using a factoring approach, we do end up getting both the half and the 0. So when we see equations like 2 cosine squared x is equal to cosine x, we don't want to think division, we want to think factor. Okay, so let's go ahead and work through this problem using our cosines. So we have 2 cosine squared x is equal to cosine x. So instead of dividing, we're going to pull that cosine x over. So it's 2 cosine squared x minus a cosine x is equal to 0. And we're going to pretty much follow the same algebra. We're going to pull out a cosine x. When we factor that out, we're going to be left with a 2 times the cosine x remaining, and then minus a 1. And again, all that's equal to 0. So two things multiply to give you a 0. That means one of them or both of them is 0. So cosine x is equal to 0, or 2 cosine x minus 1 is 0, which the 2 cosine x minus 1 equals 0 is going to turn out to be cosine of x is equal to a half. Okay, so we have basically two equations here that we need to solve for x. We have the cosine of x equals 0, and we have the cosine of x equals a half. So we need to find all the solutions for both of these. Okay, let's go ahead and start with the cosine of x equals 0. So on the unit circle, where is cosine equal to 0? So remember, cosine is the x-coordinate on the unit circle, so that's the 2 points on the y-axis. So 0, 1, and 0, negative 1. So at 0, 1, that is an angle of pi over 2, and at 0, negative 1, that's an angle of 3 pi over 2. So those are both between 0 and 2 pi, and so we can express all of our solutions as pi over 2 plus 2 pi k, and x equals 3 pi over 2 plus 2 pi k. All right, so those are the two answers, the two expressions that we get for cosine x equals 0. And then let's look at the cosine of x is equal to a half. So where is cosine equal to a half? Well, remember, again, going through the process, cosine is positive in the first and the fourth quadrant. And we know in the first quadrant, cosine is a half at pi over 3. So what is the pi over 3 angle in the fourth quadrant? Again, using our unit circle, it's going to be a 5 pi over 3. So those are the two angles that we get. So if we write those out and expressing the infinitely many solutions, we'll have x equals a pi over 3 plus a 2 pi k. And then we'll also get a 5 pi over 3 plus a 2 pi k. So all four of these answers together represent our solution. Okay. So if we wanted to write out the infinitely many solutions, we'd have to list all four of those out. If you wanted just the answers between 0 and 2 pi, it's the pi over 2, the 3 pi over 2, the pi over 3, and the 5 pi over 3. This should be a 3 here. All right. Now, technically, I'm not too worried about this, but in case you see it here, the pi over 2 and the 3 pi over 2, those are both a distance of pi apart. So from pi over 2 to 3 pi over 2 is a distance of plus a pi, and from 3 pi over 2 up to 5 pi over 2 is another distance of plus pi. So we could take these first two and rewrite them as just pi over 2 plus pi k. All right, so I could merge those together into just a single expression, but I can't do that with the pi over 3 and the 5 pi over 3. So whether you're either going to have all four answers, all four expressions as your answer, or if you merge the two, you'll have the three answers as your expression, the pi over 2 plus pi k, and then the pi over 3 plus 2 pi k, and then the 5 pi over 3 plus 2 pi k. Again, it doesn't matter to me which way you do it, but just in case you see an answer like that in the lab manual or something like that, or in WebAssign, hopefully that'll kind of help you know where that comes from. All right, let's look through just a couple more examples here. So we have the sine squared of alpha plus 2 times the sine of alpha minus 3 is equal to 0. Again, before we work through all of the trig algebra here, let's just kind of write this as an equivalent algebraic equation. So let's kind of ignore all the signs and just think of them as x's. So we would have an x squared plus a 2x minus a 3 is equal to 0. So again, going back to just kind of basic factoring, since I have an x squared term, an x term, and a constant, we want to try and factor this. And if it does factor, it's going to factor in terms of 2 parentheses multiplied to equal 0. Again, that's key. Make sure you have it equal to 0 there. If it's not, you have to do a little bit of algebra to set it, make it so it is so. So again, to factor, what are the two things that multiply to give you x squared? Well, that would be x and x. And what are two things that multiply to give you a negative 3? Well, it has to be a 1 and a 3 because 3 is prime. One of them will be positive, one of them will be negative. And since the 2 is positive, I need the bigger number over here, so the 3, to also be positive. So I can factor x squared plus 2x minus 3 into the factors x minus 1 times x plus 3. Again, that's equal to 0. And so that means x minus 1 is equal to 0, or x plus 3 is equal to 0. So we get x is equal to 1, or x is equal to a negative 3. Okay, so again, that's sort of off to the side there, just thinking about basic algebra. Okay, so let's repeat this whole process using our signs. So we have a sine squared alpha plus a 2 sine alpha minus 3, and we can factor this into 2 parentheses, that when they multiply together we get 0. So what are the two things that multiply to give you sine squared? Well, it has to be sine of alpha times another sine of alpha. What multiplies to 3? We have a 1 and a 3. Since the 2 is positive, it has to be sine of alpha plus 3, and then sine of alpha minus a 1. And we're multiplying those and getting 0. So we can split that apart. We have sine of alpha minus 1 is equal to 0, which means sine of alpha is equal to 1. Or we have the sine of alpha plus 3 is 0, which means the sine of alpha is equal to a negative 3. Okay, so we have all the simplifying done. We've done all of our algebra. We just need to apply our unit circle now. So when is sine equal to 1? So remember, sine represents the y coordinate. The only point in the unit circle where we have a y-coordinate of 1 is on the y-axis, the positive y-axis. That's the coordinate 0, 1. And the angle for that is pi over 2. So that means right now we have theta is equal to pi over 2. And since we're wanting to find all solutions, we'll just put a plus 2 pi k on there. If I only wanted the solutions between 0 and 2 pi, I would just say pi over 2, and that would be it. All right, let's talk about our second equation over here. We have the sine of alpha is equal to a negative 3. So this is actually going to turn out really nice for us. We just got to think about it a little bit. If you think about the unit circle, remember sine represents the y-coordinate. What's the highest y-coordinate we have? It's the point 0, 1. So the highest sine ever gets is 1. What's the lowest it ever gets? If you go to the bottom of the circle, it's the point 0, negative 1. So the highest sine ever gets is 1. The lowest it ever gets is negative 1. If you go back to the trig graphs, the sine graphs that we saw a few weeks ago, the sine wave goes up and down and then back up to the origin. So it has that kind of shape. And its range is from negative 1 to 1. Remember, so it doesn't go below negative 1 and it doesn't go above a positive 1. So how is it possible to get sine equal to a negative 3? Well, the answer is that it doesn't. So this particular part of the equation does not give me a solution, or you could say it does not exist. Okay, so there is no solution for this half of the equation, which means the only solution I have to worry about, the only solution to my original equation, is my pi over 2 plus 2 pi k. All right, last example. Again, dealing with factoring, we're going to add a term onto this one. So we have the tangent cubed of x plus the tangent squared of x minus 3 tangent x minus 3 is equal to 0. Okay. So let's try to do this again, just knock off all the tangents. So let's think of this as x to the third plus x squared minus 3x minus 3 equals 0. And the x's in my algebraic equation represent tangent x, where tangent x over here is a different x. But anyway, we're just playing around here. So how do we factor x cubed plus x squared minus 3x minus 3? Some of you may remember this, but we're going to use a process called factoring by grouping. Okay, so we're going to pair up our terms. There's 4 terms, we're going to pair them up. So what can I pull out? What do I have common between x to the third and an x squared? Well, I can pull an x squared out of both of those. And if I pull an x squared out of those, we're going to be left with an x plus a 1. All right, and what can I pull out of a negative 3x minus 3? They both have a 3, and they actually both have a minus or a negative. So let's pull out a minus 3. So if we pull out that minus 3, we're left with an x plus a 1 again. Okay. And so now we have 2 groups. We have the x squared times x plus 1, and then we have the minus 3 times another x plus 1. Well, those x plus 1s, those are common factors, so we can pull those out front just like we did before. So we're going to pull out an x plus 1, and we're going to be left with an x squared minus 3. And that will all be equal to 0. And then we could solve the equation from there. So that's going to give us x plus 1 is equal to 0, which means x is equal to a negative 1. And then we're going to have x squared minus 3 is equal to 0, which means x squared is equal to a positive 3, which means x is equal to a plus or minus square root of 3. Okay, so we're going to do the same thing using the tangents that we just did using just the x's. So we're going to follow the same algebraic process just using tangents. So we're going to group the tangent cubed and the tangent squared, and then we're going to group the negative 3x minus the 3. So we're going to pull out a tangent squared x, which leaves a tangent x plus 1. And then we're going to pull out the minus 3, which is going to leave another tangent x plus 1, still equal to 0. Both of these terms now have a tangent x plus 1, so we're going to pull that out front. We have a tangent x plus 1 times a tangent squared x minus 3, still all equal to 0. And then we're going to split those apart. So we have the tangent of x plus 1 is equal to 0, which means the tangent of x is equal to a negative 1. Or we have the tangent squared x minus 3 is equal to 0, which means the tangent squared x is equal to a positive 3, which means the tangent of x could equal a positive or a negative root 3. And let's split that apart now. So that means we have or the tangent of x is equal to a positive root 3, or the tangent of x is equal to a negative root 3. Okay, so in this example, we actually have 3 equations that we need to check their solution. And then we want to express all of our answers. So let's go back to tangent of x equals negative 1. So we know tangent is positive in the first and the third quadrant, and it's negative in the second and the fourth. So we need an angle in the second and the fourth quadrant. And we know that since tangent is equal to 1, it's equal to y over x. That's equal to it's going to be at our 45-degree angle, or our pi over 4 angles. So if we look at pi over 4 in the second quadrant, that'll be 3 pi over 4. And in the fourth quadrant, it's going to be 7 pi over 4. So we have 2 angles. All right. If we look at the tangent of x equals square root of 3. Again, let's draw our unit circle here. Think of square root of 3 as square root of 3 over 1. It's positive, so that's going to be somewhere in the first quadrant, but it's also positive in the third quadrant, sorry. So first and fourth. And remember, tangent is sine over cosine. So when is sine root 3 over 2? Again, this is kind of the way I do it. Where is it? 3 over 2 and 1 over 2. That would be at the pi over 3 angle. So we have a pi over 3 in the first quadrant, and then we're going to have a 4 pi over 3 in the third quadrant. So we got 2 more. And then the last part here is tangent of x equals a negative 3. Well, same basic thing we just looked at, but it's negative, which tangent is negative in the second and fourth quadrants. But it's still basically just a root 3 over 1. And so that's going to put us at pi over 3 angles in the second and fourth quadrant. So 2 pi over 3 and 5 pi over 3. So between 0 and 2 pi, we have 6 answers. Okay, so let me just list all 6 of those out. So between 0 and 2 pi, we have x could equal, let's try and list them off in increasing order. So we could have pi over 3. We could have 2 pi over 3. We could have 3 pi over 4. We could have 4 pi over 3. And then we could have 5 pi over 3. And then lastly, we would have 7 pi over 4. Now, if you don't list them out in order, that's fine. But so we have 6 possible answers here. Okay, and if you're just trying to list the answers from 0 to 2 pi, you have to list all 6. Okay, but we just want to list the infinitely many solutions. So let's remember how we do infinitely many solutions with tangent. Okay, remember the nice thing with tangent. Tangent has a period of pi. So that means going from our first pair of solutions, 3 pi over 4 and 7 pi over 4, from 3 to 7 pi over 4 is a distance of pi, where you're adding pi. And then coming around back to the starting point is another addition of pi. So we don't need to list both of these solutions. So we could just talk about x equals, we only have to list that first one. So 3 pi over 4 plus, and we're going to do plus pi k. That's the first one. For tangent, we have pi over 3 and 4 pi over 3. Well, again, from 1 pi over 3 to 4 pi over 3 is a distance of pi. And then from 4 pi over 3 to the next pi over 3 would also be a distance of pi. So we don't need to list both of those. If we're expressing all of them, we can just say start at pi over 3 and let's go a distance of pi k. And then the last one, if we went from 2 pi over 3 to 5 pi over 3, again, that's a distance of pi from there to there. And then from 5 pi over 3 back to the 2 pi over 3 is another distance. That's another addition of a pi. So we don't need both of them, we only need the first one. So we could say 2 pi over 3 plus pi k. All right, and so we could express the infinitely many answers using just these 3 expressions. If we wanted to list all the answers between 0 and 2 pi, then we have to use all 6 of them. We have to give the 6 specific values. But again, for all solutions, we only needed the 3 simplified expressions. And there are some examples where you could take all 6 of those plus pi k's or all 6 of the plus 2 pi k's and reduce them down into one answer. It just depends on the symmetry that's involved and where the answers are located. But anyway, so that's solving equations. Again, we have not used any identities. It's just basic algebra, and then square roots, and then factoring. And you can use any form of factoring, but we're not going to get real crazy here. And then in another few weeks, we'll come back and we'll revisit solving equations using all the identities.